Shivpur. He completed the Master of Production Engineering from Jadavpur University, stood first class first in the Master of Production Engineering course and received University Gold Medal. He completed PhD from Jadavpur University. He also received Young Scientist Award from DST, New Delhi in 2002. He was the principal investigator of DST sponsored project and CSIR sponsored research project on the area laser beam machining of engineering ceramics, and also DST Pursuit project of Jadavpur University. He completed PARC sponsored research project on electrochemical micromachining as co-principal investigator. He is co-principal investigator DST sponsored research project on wire electrochemical micromachining. He has published about 75 journal papers in international and national level in the area of advanced manufacturing technology and presented about 126 research papers in reputed national and international seminar and conference. Under his supervision, 13 PhD theses has been awarded and 8 PhD theses are in progress. He has visited reputed international institutes like Cranfield University, UK, National University of Singapore, Polytechnic University of Hong Kong, Asian Institute of Technology, Bangkok, and IIUM, Malaysia. He is and co-author of the book entitled Modern Manufacturing Technology that published by Elsewhere. I request Professor Vishwanath Dalai sir to preside the session. Today he will deliver the talk on recent advances in laser beam machining. I hope all the participants will interact in the interactive session at the last of his presentation. Sir, please, sir, preside the session.
Okay. Good afternoon to all of you. Dear Professor Chittaranjan Deo and Professor Santosh Kumar Sahu and other coordinators of AICTE sponsored Atal online faculty development program on recent advancement in manufacturing processes, RAMP 2021. So first of all, I thank you for inviting me to deliver the lecture in this FDP program. So dear participants, my topic of presentation is recent advances in laser beam machining processes. And laser beam machining is a energy based advanced subtractive manufacturing, that is machining process. Now I want to present my slideshow. Minimize করতে না। I think it is visible. Hello?
Yes, sir. Yes, sir.
Okay. So topic of my presentation is recent advances in laser beam machining. Now content of my presentation: first, introduction to laser generation, then I will discuss about various types of laser for machining application, and then various laser micromachining processes, laser assisted machining processes, and finally conclusion. Now, I will discuss briefly about the fundamentals of laser and laser generation. So full form of laser is light amplification by stimulated emission of radiation. We know laser light a beam of photon, and it is coherent and monochromatic, and it is highly directional, and it has high brightness with very high power intensity. A laser beam basically useful for machining purpose, and it is nothing but the emission of radiation and basically emission of photon, beam of photon, and in a narrow coherent beam which consists of single wavelength in the visible, infrared and ultraviolet region of spectrum. So laser may be IR laser, infrared laser or ultraviolet laser. So it is basically coherent and monochromatic beam of photon. Now laser beam and ordinary light beam, these are different. Laser light is coherent and monochromatic in nature, but ordinary light is incoherent and it emits in almost all direction, usually over a wide spectrum of wavelength. So laser beam is monochromatic, that means it has single wavelength, but ordinary light emits over a wide spectrum of wavelength. So that is the difference. It is not, ordinary light is not monochromatic, but laser light is monochromatic and coherent. Coherent means the photons are emitting with constant phase difference. And laser light or laser beam can be focused down to a very small spot size in the order of few micron. That's why it is useful for micro machining applications. And because of very small spot size, the energy intensity is therefore very high. And because of high energy intensity means energy per unit area. So spot size area is in the micron range. So cross-sectional area is very, very less. That's why the energy intensity, that is energy per unit area, is very, very high. And that is required for machining purpose. So laser beam can be applied as a high energy intensity beam, and it has many areas of application in manufacturing, in measurement, or in other non-manufacturing applications also. But ordinary torchlight cannot be focused down to a very tiny spot. So if you want to focus the ordinary torchlight, then it will actually diverge. But the laser light can be focused to a long distance. Its angle of divergence is very, very less. So if you go through the fundamentals of laser generation, then there are some lasing medium when it is excited. Excited means when it absorbs energy from source of excitation, then it is excited and goes to the higher energy state, higher energy level. But at the higher energy level, at the excited state, the lasing medium cannot stay for long time. So after a certain time, it will go to the metastable stage or ground state, and when it is coming back to the ground state, then it emits photon. It emits energy in the form of photon. So lasing medium may be different for different type of lasers. Say if you say solid state laser, neodymium or erbium, ytterbium, these are the lasing medium. So when these lasing medium is absorbing energy, so it is absorbing the energy from the optical source or from the discharge energy So it goes to the higher energy level when it is excited, but when it is coming back to the ground state, then it emits the energy in the form of photon. So these emitted photons has constant phase difference and it is monochromatic. That's why it is laser beam. So this fundamental of laser generation is almost same for all the laser, say it may be solid state laser or gas laser, but the excitation mechanism is different. But all lasing mediums should be excited, otherwise you cannot get the energy or beam of photon with special properties, that is laser. Now if you want to apply this laser for machining applications, then what are the requirements? Now laser is generated, but it should be moved between these two mirrors. So this is basically the optical resonator. So this is fully reflective mirror, 100% reflectivity, and this is partially reflective mirror. So this beam of photon actually oscillate between these two mirror, and its energy is increased, and finally it comes out from the partially reflective mirror, and then it is focused by means of lens. So lens is mainly used for focusing purpose. Okay, so if you focus it, then the spot size here you see at the focal point is very less, and energy per unit area, that is the energy intensity, is very high. And this laser beam should be focused on the workpiece surface to utilize its energy. And then if you want to go for machining application, then you have to move the workpiece along XY direction, and for focusing purpose the lens can move along the Z direction, and this workpiece is placed on XY table, and this is controlled by CNC controller. So this is the laser generation as well as the machining system, but the lasing medium may be different, or the source of excitation may be different. Now source of excitation, it may be optical pump system, say diode pump. Diode pump is also diode laser is used as a source of excitation of energy, or krypton arc lamp. Krypton arc lamp which emits photon. Now this lasing medium absorbs the photon and then it is excited, and then finally it emits the beam of photon with special characteristics, that is laser. So for source, as a source of excitation, you require the lamp. It may be krypton arc lamp, or the diode laser itself can be used as a source of excitation. Then nowadays these systems are coming, the diode pumped 5-hole laser, diode pumped Nd:Arc laser, etc. So this is basically the solid state laser, but for gas laser the electrical discharge is required between the anode and cathode, and from there the energy is utilized to excite the lasing medium. Say for CO2 laser, CO2 gas molecules are to be excited, and for that you require to consider the discharge cell, electrical discharge cell, and cathode, anode, etc. are required. I will discuss later on. Now if we quickly go through the background of laser generation, in 1917 Einstein had showed that lasing action should be possible in his paper on quantum theory of radiation. Now, Gordon Gould was the first person to use the word laser in 1959. So he is the person who uttered this term laser. Now, in 1960, Dr. Meyerman invented the first ruby laser. So this is the solid state laser, and Dr. Theodore Meyerman, he has invented first ruby laser. Then thereafter, a lot of developments in late 70s, YAG lasers with power in the order of 100 watt and CO2 laser. So this CO2 laser was developed by Dr. C.K.N. Patel in Bell Lab. CO2 laser has high power, 1000 watt. And then in 1970, first continuous wave diode laser. Diode laser was developed with less power. So semiconductor diode laser, which is used in printer as well as in pointer. So this diode laser was also developed that time, 1970. Then in 1980, fiber laser technology was available using erbium doped single mode fiber. So erbium, this is the lasing medium. For CO2 laser, CO2 gas molecules is the lasing medium. For ND-YAG laser, ND, neodymium is the lasing medium. Okay, so lasing mediums are different, and gradually the lasers are no longer treated as laboratory research equipment, and laser manufacturing has become a multi-billion-dollar industry. And gradually laser is applied in many fields of manufacturing, such as inspection, measurement, testing, medical device fabrication, material processing, surface treatment of diverse range of materials. So there are different types of materials, from plastic to diamond, plastic, metal, glass, ceramic, composite, diamonds. All the materials can be machined or processed by laser, and list of application is endless. Now, for different application, different manufacturing applications, we require different laser beam intensity. Okay, as I told, laser intensity means laser power per unit area, watt per centimeter square. So here, for machining, you have to melt the material and vaporize the material. So for that, we require high power and high power intensity. For machining, we require 1.5 multiplied by 10 to the power 6 to 1.5 multiplied by 10 to the power 8 watt per centimeter square. So 10 to the power 6 to 10 to the power 8 watt per centimeter square. So here, melting and vaporization, sometimes laser ablation, that means you directly melt, you directly vaporize, no melting. So energy intensity is so high that some of the materials are directly vaporized from solid. So without melting, the vaporization of the material from solid, that is laser ablation. So that is also the material removal mechanism while you are going for machining or removing the material. So for machining, we require high power intensity. But for welding, where we are not removing the material, we are joining the material. So you are just the materials are in the same molten state. So for that, we require the comparatively less energy power intensity, that is 1.5 into 10 to the power 4 to 10 to the power 5 watt per centimeter square. But for forming means bending, extrusion, etc. So the power intensity 10 to the power 3 to 10 to the power 4 watt per centimeter square. And for surface alloying, it is 10 to the power 4 to 10 to the power 5 watt per centimeter square. Okay, so we are mainly focusing for machining. So for machining, melting, vaporization, as well as direct vaporization from solid are the mechanism. But for ceramic material, thermal spalling is also another mechanism. So for that we require high laser beam power intensity, that is 10 to the 6 to 10 to the 8 watt per centimeter square. Now advantages. What are the various advantages? High productivity, no contact processing. So here it is an advanced non-traditional machining process, and here laser beam is the tool. So no other tool is used here. So tool related problem you can overcome. No contact processing. Okay, no tool, no contact. But laser beam should be absorbed by the material. That is the requirement. And elimination of finishing operation, because this process has high surface finish, so no post processing is required. And adaptability to automation. So this laser system is CNC and it is automatic control. And reduce processing cost. Cost of processing is less, but initial investment cost is high. That is the disadvantage. But processing cost is not high. And product quality is very high, and greater material utilization, that is very, very important. We can utilize the material effectively. The wastage is less, because if you want to go for cutting, then cut width is micron dimension, because laser beam size is in the micron range, so cut width is in the micron range, so less material is removed, but it can cut the workpiece with larger depth. So greater material utilization, because wastage of material is less, because that width of card or carp width is less. And minimal heat affected zone. It is a thermal process, heat affected zone is there, but if the process is ablation, that means directly solid to vaporization, then heat affected zone will be less. But if it is melting and vaporization, then the heat affected zone will be large, but you can control. Compared to the other flame cutting or plasma cutting operation, the heat affected zone is less. Then high speed, okay, it is very faster process, 10 to 100 millimeter per second speed. And transportability, laser beam can be transported from one place to another place. For remote area, you can apply this laser beam, particularly for cutting nuclear fuel rod, etc. No chemicals required. For ECM, chemical machining, you require chemical, but here no chemical. And selective material removal, you can selectively remove the material from the region where you actually require. So selectively you can remove the material. From the top you can remove the material, from the bottom you can remove the material. So selectively you can remove the material. So these are the advantages of laser beam machining. Now these are the general applications. So it can cut very hard material like diamond. So diamond jewelry industries, laser machine is applied. Then it can be useful for fabricating IC or printed circuit board, and it can be used for processing nuclear fuel rod, cutting of nuclear fuel rod. Then non-machining application like welding is also another application, and it has wide application in pointer, printer, plotter, etc. Now medical device fabrication, laser has wide application, cutting of stain, fabrication of stain, marking on stain. So laser has wide application in medical industry. Now, as I have told you that laser beam is a source of energy, so it can be applied for heat treatment, surface hardening, alloying, cladding, cleaning, etc. And I will mainly focus on micro machining applications, micro drilling, micro cutting, micro grooving, micro turning, thread cutting. Not only for micro hole generation, it can be useful for large hole generation, that is trepanning. And it can be applied for drilling minute hole in nozzle, fuel nozzles, and also it can be useful for turbine cooling hole, etc. And artificial ceramic hip joints, it has wide application. And it can also be applied for dressing of grinding wheel, So these are the general applications in the field of manufacturing, machining, as well as non-machining applications. Now, material removal mechanism. So for laser beam machining, the laser radiation is first absorbed by the material surface. So material should absorb the laser energy. Otherwise, it will be useless. Okay. So the material should absorb the laser radiation, or it should absorb the energy of the laser beam. Then only its temperature will be increased. Okay. And if the temperature is above the melting point, then it will melt and then it will vaporize. Okay. So melting vaporization is the mechanism for long pulse laser, that microsecond pulse duration laser or millisecond pulse duration laser. Okay. Now here another thing is very important, that the thermal properties, absorptivity, reflectivity, transmissivity, these properties are very, very important. As laser beam machining is an advanced non-traditional machining process, here mechanical properties are not important. Mechanical properties, say ductility, toughness, etc. of the material are not important. Here the important properties are absorptivity. So the laser energy should be absorbed. So absorptivity of the workpiece material, that is very, very important. Obviously, if absorptivity increases, then reflectivity or transmissivity will be less. So it should not be applicable for highly reflective material. But glass, although glass has high reflectivity, but glass can be machined at the machining temperature. Here, in case of laser beam machining, the machining temperature is very high. So at higher temperature, the reflectivity of the glass decreases. So although at normal temperature, reflectivity of the glass material is very high, but at the working temperature, where the in the machining zone, the temperature is very high. With high temperature, the absorptivity increases, reflectivity decreases. That's why the laser can be applied for machining glass also. So glass machining is possible with proper control by laser beam machining. Okay. So if the surface is highly reflective, then it is difficult, although at high temperature it is possible, because at high temperature reflectivity decreases, absorptivity increases. So workpiece material should be such that it will absorb the laser beam energy at the working temperature. That is the requirement. So melting vaporization, as I told, for long pulse laser. But if the laser is short pulse laser, okay, short or ultra short pulse laser, say nanosecond laser, that means pulse duration is nanosecond or picosecond or femtosecond. So for this type of laser, that energy applied on the workpiece material with high intensity, with high peak power for very less time, so there is no time for melting. So without melting, the material is directly vaporized from solid. So that is known as laser ablation. So this is another mechanism. And if the laser ablation is there, then all the thermal related problem, which is occur due to melting phase can be eliminated. Particularly for micromachining, where we don't require any thermal damage. So for that case, we require very short pulse laser, and laser ablation is the material limbal mechanism. Now thermal spelling, this is basically for ceramic material where thermal stress is higher than the bonding stress. So removal of grain by breaking the bond as induced thermal stress exceeds the bond strength. So this is the thermal spelling. This is for ceramic material. And here, to assist the material limbal, we require the assist gas jet. So additional assist gas jet of very high velocity, which is applied, which exerts momentum on material, leading to ejection of the molten material. So it assists the material limbal because that there is chances of resolidification of the molten material. So to avoid this, when the material is melt and then immediately it should be removed. So for that we supply the assist gas jet. Okay, so these are the material limbal mechanism. So mainly melting vaporization and ablation, and for ceramic, thermal spelling. Now here you see, this is the machining with long pulse laser. So this is the laser and duration is long, millisecond or microsecond. Then there is melting, so lot of thermal related problems are there, micro cracks, then heat affected zone, damage to the adjacent layer, recast layer, resolidified layer. So this is not desirable. But if you go for very short pulse laser, the pulse duration is very short, but the energy intensity is very high, peak power is very high, because there is one relation that peak power equal to average power divided by the product of pulse frequency and pulse duration. So if the pulse duration decreases, then peak power increases. So peak power means gigawatt range, kilowatt or gigawatt, megawatt or gigawatt range. So gigawatt range power for very short duration, nanosecond or picosecond or femtosecond duration, then there is no time to melt, directly solid is vaporized. So no melting means no melt zone, no micro crack, no thermal damage. Okay, so all the problems are eliminated when you are using short pulse. So selection of laser is very important when you are going for machining, micro machining, especially micro machining application. Now I will discuss different types of lasers. Nd:YAG lasers. Nd means neodymium. This is the lasing medium and it is doped in YAG crystal, yttrium aluminium garnet. So this laser has excellent properties like high peak power, good focusing characteristics, small pulse duration and small wavelength. So here wavelength is 1064 nanometer wavelength. This is the solid state laser, and this laser can be transported by fiber optics cable. And this laser system integrated with CNC control has great potential for wide use in machining application. So we are mainly focusing on machining application. So Nd:YAG laser can be used for machining application, micro drilling, profile cutting, marking. Marking is by removing the material, marking by machining basically. And groove, micro grooving, you can produce the groove of micron width or micron depth. And then turning, laser turning, so you can remove the thin layer or micron layer of material from the cylindrical workpiece. So that is the laser turning. So laser, Nd:YAG laser can be used for non-machining applications also, such as welding. Laser welding is common. Laser micro welding is very common nowadays. Forming, laser bonding, laser bending, laser extrusion, etc. Then surface treatment such as surface alloying. So in case of surface alloying, we are melting the surface and adding the alloying elements. Surface cladding is basically thick film layer deposition. It is not coating. Coating generally thin film, but here thick film or layer deposition over the base material. It is a cladding, laser surface cladding. Laser surface hardening, heating and cooling, increase the hardness. Surface glazing, okay, and then surface cleaning. You can clean the surface. You can clean the coating or rust portion. So where you have to control the laser beam, focusing condition, pulse frequency, pulse duration, etc. So it can be used for machining application that I want to focus in this lecture, but it can be used for non-machining applications also. Now this is the schematic diagram of INDIAG laser system. So there is one lasing head where Kiptronach lamp is there. So this is the source of excitation, Kiptronach lamp. Kiptronach lamp emits photon, and this photon is absorbed by neodymium atom, which is doped in YAG rod. So there is one elliptical cavity. Elliptical cavity has two focus. In one focus, lamp is present. Another focus, this INDIAG rod is present. When the Kipton lamp is ignited, it emits photon. This photon is absorbed by the neodymium atom and goes to the higher energy state. But at the higher energy state, it cannot stay for a long time. Again, it goes to the metastable or ground state, and it will emit the energy in the form of photon with special characteristics of laser. So lasing laser head is very important part of this any laser system. After that, it is passing through the lens. Okay, so sorry, mirror. As I told that there are two mirror. No, one is back mirror. This is the back mirror or rear mirror, 100% reflection. So laser cannot move this way. It will back to this path. It will follow this path, and this is the front mirror. This is the front mirror, partially reflective mirror. So between these two mirror, it will oscillate and it gets its energy. Okay, and then another important switch is there, Q switch. The Q switch is the quality switch, which is mainly converts the continuous wave laser to pulse laser. Continuous wave laser is used for welding application. So average power is less, but to get the pulse wave laser where peak power is high, because peak power is equal to average power divided by the pulse frequency into pulse duration. So here you have to convert continuous wave into pulse wave, but pulse wave laser is the requirement for machining of metal. So for that you require Q switch, and then intercavity aperture are there to move the laser in this particular direction, and finally it is bended at 90 degree, and then it is passed through the lens. This is the important component for focusing purpose. The lens has a particular focal length, so this lens can be moved up and down. So there will be movement along the Z direction to control the position of the focal point. So this should be focused on the workpiece surface to utilize the maximum energy, because the energy efficiency is very less for laser beam machining. Okay, so you have to utilize the energy of the laser beam. So from which region you want to remove the material, at that particular region you have to focus. Obviously on the workpiece or job, and job is mounted on XY table, So for machining, you have to move the job as per requirement along the X or Y direction. And for focusing, you have to move the lens along the Z direction. Now, every system has this type of arrangement: laser generation unit, okay, and then beam delivery, beam bender or focusing unit, and then cooling unit. Sometimes for high power laser we require water cooling system. For low power laser we require air cooling system. And work holding table CNC controller for X, Y, and Z axis movement. So these are the requirement for CNC laser system, machining system. Now this is the schematic, photographic view. So this is the portion, this is the machining table. Workpiece is kept and it can move along XY direction. And this is the head, laser head, where laser is generated and it is bent at 90-degree angle. And this is the camera. Camera actually, this is the charge coupled device camera. Camera actually grabs the picture of the workpiece surface. Now, if the picture is very much clear, actually their lens is in between. So if the workpiece picture grabbed by the camera is clear, then we can assume that the workpiece is perfectly focused. That means the laser focus point is on the workpiece surface. Now this view is shown in this CCTV. This is CCTV, this is not CCD-TV, CCTV. This is closed circuit TV. And this is charge coupled device camera. Okay. Now for laser generation, this is actually that lamp pumped laser generation system. So Q switch is there for pulsing, and then this is a Kryptonarc lamp controller. So it will control the average power, and we can control the pulse frequency. For this system, pulse duration is fixed, 120 nanosecond. And this heat exchanger is used for cooling purpose, cooling the laser head, cooling the Q switch, which switch is used for pulsing. And this compressor, air compressor, is used to supply the assist air. So in our case, we have used air as the assist gas, but we can use that inert gas also. Yeah. Helium or argon gas can be used as the assist gas, okay, to avoid the oxidation. But here for our experiment we have used air. So this is the chiller unit to supply the chill water, and then there is heat exchanger. Actually in this laser head or Q switch we supply the deionized water. So there is heat exchange between the ordinary water, cool water, to the deionized water. So this is the system, and this is the CNC controller. Okay, for X and Y axis movement, which is imparted to the tool, workpiece, and Z axis movement provided to the lens for focusing purpose. And this is the voltage stabilizer. Now applications. As I told that material processing, okay, different types of material processing, material removal also for wide range of engineering materials. So it may be plastic, PMMA, polymethyl methacrylate, or it may be diamond or metal, any kind of material, glass. Okay. Now fabrication of medical devices. I'll show some slide that for cutting of stent, cardiovascular stent, this Nd:YAG laser system can be useful, or for making some complicated micro features on the medical implant, we can use this laser beam machining. Marking, okay, marking is also one of the application. Marking by machining. Marking may be of two types. One is by surface modification, by removing the material. So laser beam machining can be applicable for marking by removing the material. Then micro machining, micro cutting, micro drilling, micro grooving, micro turning, dressing, etc. Now CO2 laser system. So CO2 laser system, here, as I told initially, that electrical discharge is the requirement as a source of excitation of energy. And carbon dioxide molecules, these are used as a lasing medium. So CO2 molecules absorbs the energy, and other gases, helium is used for cooling purpose because there is cold emission. And then nitrogen is used for as a charging gas. So nitrogen actually transmit the energy to the CO2 molecules. So as we call it as CO2 laser system, but other gases are required. Okay, carbon dioxide gas is the lasing medium, but nitrogen, helium gases are required. And you have to produce one that cell, discharge cell. For that you require cathode, anode, and two mirrors. So these two mirrors are requirement for all the laser generation because it makes optical resonator. So full mirror means fully reflective mirror, 100% reflectivity mirror, and this is partially reflectivity mirror. And then finally it is coming. But here the CO2 laser has high value of wavelength. Okay, so here the wavelength is 10,640 nanometer. Okay, so here the wavelength is large. Okay, compared to Nd:YAG laser. Okay, so although it is also IR laser, infrared laser, CO2 laser is IR laser, but here wavelength is long, 10,640 nanometer or 10.6 micron. But for Nd:YAG laser, it is 1.06 micron. Okay, so if the wavelength is large, then the spot size is also large. I will show you some relation, but for micro machining application, this CO2 laser is not useful, but for other applications it can be useful. So as I told, the CO2 laser system where carbon dioxide gas is 10%, nitrogen 30%. Nitrogen is used as a charging medium and helium as a coolant 60%. Okay, so nitrogen levels can be charged by means of high voltage DC or radio frequency charging, and here the efficiency is 10 to 15%. And nitrogen molecules are charged and they transfer energy to the carbon dioxide molecules, and carbon dioxide molecules absorb the energy. This is the lasing medium and it emits the laser beam in the IR infrared region, but here wavelength is 10.6 micron. Okay, now this is the photographic view. This is the laser generated and this is the laser generation system, and finally it is coming on the workpiece. Now it has wide applications for machining, surface engineering. Okay, and this CO2 laser can be absorbed by our human cell. Okay, so that's why CO2 laser is useful for surgical applications. So it can be absorbed by water-based compound it can be absorbed by biological tissue. So it has wide application in the biomedical field, laser surgery, skin resurfacing, laser facelifts, etc. CO2 laser can also work well on wood cutting, acrylic, plastic, and many other applications. So these material can absorb CO2 laser, and it can also be used for metal machining, marking on stainless steel, okay, on coated materials, etc. Now, 5R laser. The 5R laser is IR laser, and it is similar to Nd:YAG laser, but the lasing medium is doped in fiber optics cable. Okay, so you see, it has different core, inner core, outer core. Okay, so this inner core is ytterbium doped. Ytterbium, YB, this is the lasing medium, and it has outer cladding also. Okay, so this fiber cable has different layer. Okay, different layer of coating, and there will be requirement of 2 mirror also. Okay, so this is the source of excitation. So it may be diode laser, diode pumped or lamp pumped, and then there are 2 mirrors. Okay, and finally this laser beam is coming out. The 5R laser is solid state laser, as I have mentioned. Wavelength is similar to Nd:YAG laser, 1064 nanometer, and ytterbium atom acts as a lasing medium. Diode laser is used as a pump source, so then is a diode pumped 5R laser. Diode pump 5R laser is used for machining applications, and pump radiation is launched into the 5R core and gradually absorbed over the 5R lens and converted into the laser radiation. So here optical fiber is a cylindrical dielectric waveguide made up of silica glass. Okay, and 2 mirrors are there to make the laser cavity, as I told. And if you require high power laser, then obviously you have to use ytterbium, or erbium can also be used. But for high power, you require ytterbium as the lasing medium. Now this is the system, diode pump 5R laser system. Okay, so this is the diagram. So here the laser head, 5R laser is generated, and this is the fiber optic cable. It can be used to transport the laser beam, and then there is a collimator. It will control the diameter of the laser beam. Okay, so it is bent at 90 degree, and then finally it is focusing through the lens. Okay, so this is the focal length. You can control by changing the lens, and then this is the coaxial nozzle system. Through this you can supply the assist gas. Okay, and here you see that beam diameter, input diameter is large, about 9 millimeter, but after focusing, the spot diameter is 20 micron or 21 micron. So this is the speciality of the laser beam. You can focus down to a very teeny spot, 20 micron. So this 20 micron laser beam can be useful for micro machining, micro drilling, micro cutting, etc. Now this is the laser head. This is CCTV, closed circuit TV, and CCD camera is there. CCD camera is mainly for focusing purpose, whether it is perfectly focused or not. That means the spot is on the workpiece surface or not. And then laser Z-axis movement for moving the lens or focusing, and then XY table movement for moving the workpiece, and then it is connected, integrated with the PC, and this is the compressor to supply the air. Air is used as a assist gas. Now here you see this is a pulse laser wavelength, as I told. Then mode of laser beam is TM00, transverse electromagnetic 00. This indicates the circular beam. So here in our system we have circular beam. Initial beam diameter 9 millimeter, but spot diameter is 21 micron. Average power 50 watt, but peak power is very high in the range of kilowatt. And pulse duration 120 nanosecond, pulse repetition rate 50 to 100 kilohertz, and output fiber length is 3 meter. Now another laser, that is the excimer laser. Excimer laser. So excimer laser, this is also gas laser, and this is derived from the excited dimer. So in this case, two gases are used. Okay, two gases. One is halide gas, fluorine or chlorine. Another is rare gas, argon or krypton. So one combination you can consider, say, argon and fluorine. This is one combination. So in this laser generation system, when two gases are excited, argon and fluorine, then these two gases are excited by absorbing the energy from electrical discharge, and then excited dimer is formed. That is the excimer, excited dimer, ARF. But at this excited state, this excited dimer cannot stay for long time. These will be separated, and when these are separated, then these are emitting the energy in the form of photon. And this beam of photon with special characteristics, constant phase difference and single wavelength. So that is the laser. And here the wavelength of laser is 193 nanometer. Here you see that wavelength is very, very small, 193 nanometer compared to Indiac laser or CO2 laser. Okay. So this excimer laser is well applicable for micro machining. Okay. So here, when two gas molecules are excited, they are united, they are separated by breaking molecules and emitting photon with high energy. And here also the pulse duration is very, very short, 25 nanosecond, and laser ablation is the material removal mechanism. Now for different combination, you can get different wavelength laser. Okay, argon fluorine, one combination 193 nanometer, krypton fluorine 248 nanometer, xenon chlorine 308 nanometer, xenon fluorine 351 nanometer. So all are excimer laser, but different wavelength. Now another laser that is very common and cheaper, diode laser. We frequently use in the pointer or torch or other application. So as a source of excitation, diode laser is used. That's why it is diode pumped laser. Okay, but this diode laser itself can be applied for machining when it is with high power. That means small module of laser diode can be coupled to produce high power diode laser. Okay, so this is similar to light emitting diode. Okay, laser power increases as the number of electrons and holes injected across the junction increases. So this is very common laser diode, but when we are considering the different array of laser diode are stacked, array of laser diodes are stacked to produce high power in kilowatt range. So diode laser is with kilowatt range is also available. very high energy, efficiency greater than 50%. This is the main advantage. In case of Nd:YAG laser, efficiency is below 5%. For carbon dioxide laser, 10 to 15%. But for diode laser, efficiency is very high, more than 50%. And it is portable, compact, more reliable, less maintenance. Air cooling is sufficient, water cooling not required, less heat affected zone, better surface finish. And you can get small power diode laser as well as high power diode laser. It can be continuous mode or pulse mode. So it has wide application for machining, micro machining, marking, and it has wide application for non-machining also, welding, etc. And this high power diode laser used for machining of polymer, composite, controlling the power, and highly reflective material like copper and aluminium. So these highly reflective material can absorb this diode laser. Now I will discuss about the various laser micromachining processes. So I have discussed about the different types of laser for machining applications. Now laser micromachining processes. Now micromachining, as we know, that what is the range of micromachining? The dimensional range less than 1 millimeter, then you can call it as micromachining. So 1 to 999 micron, 1 micron less than millimeter, so it is micromachining range. But acceptable range for micromachining, it is 1 to 500 micron. Okay, 1 to 500 micron is the acceptable range. And micromachining is becoming day by day popular for fabrication of micro components. So there are two things. One is to create micro features on the macro or millimeter dimensional component, that is micromachining, or you can fabricate the micro component, that means thickness of the sheet is in the micron level. You are making large hole but on the micro thick component, that is also micromachining. Okay, so creating micro features, micromachining, and fabricating micro component or creating millimeter dimensional shape features on micro thick component or sheet, etc., that is also micromachining. So micro plus machining, and for micromachining you require two things. One is the unit removal should be very less, micron range, and you have to use very precision instrument, because when you are dealing with micro dimension, then what will be the tolerance limit? So tolerance limit will be at least 1/10 of 1 micron. Okay, so the precision instrument you have to use for micromachining. Now if you consider different components, dimensional range, say nano level 1 nanometer, micron 1 micrometer, meso means in between macro and micro, macro meter, dimension 1 meter, okay, 10 to the 9 nanometer, and meso means millimeter. Okay, so if you want to produce stent, cardiovascular stent, there the size is millimeter, but you have to produce micro features on that, micro group, micro features on the millimeter dimensional component. So you require micromachining. Okay, for making the micro component also you required micromachining. Okay, it has wide application in micro electromechanical system, okay, MEMS, and IC chips, etc. So these are the different products, and nowadays you have to use very light component, you have to use productive use of this material. So size, with the development of smart material, the size is reducing. So if size is reducing, then the size of the features which is to be created, that is also reducing. So you have to produce various micro features on the micro component as well as meso component. So for that micro machining. Now here you see for laser beam micro machining. So this is very important, as I told, the spot size. So spot size should be in the micron range, and there is one relation DO spot size equal to 2f lambda by D. So D is the entrance beam diameter and lambda is the wavelength. So you have to select the laser for micro machining whose wavelength is very less. Okay, then spot size will be less. Okay, so this is the relation, and for particular system length, focal length is fixed. Now there are different micro machining applications in the area of microelectronic packaging, semiconductor manufacturing, data storage device, medical devices, communication and computer peripherals, and different types of lasers can be used, mostly diode pump, solid state laser, fiber laser or Nd:YAG laser, or lamp pump, solid state laser, lamp pump, Nd:YAG laser, fiber laser, excimer laser, CO2 laser sometimes we use, and applications micro drilling, okay, micro turning, and then for medical applications also catheter hole drilling, okay, stent fabrication, orifice drilling. Okay, so different micro components, micro parts, and materials, plastic, excimer, ceramic. For excimer laser, you can apply excimer laser for plastic, ceramic, silicon. Okay, so there are different materials; those can be processed by laser. Okay, metal, ceramic, plastic, diamond, glass, silicon. Okay, so from soft to hard material, the laser can apply it. Now laser micro drilling, as I told you earlier also, there are different types of drilling. One is single shot drilling. So if the thickness of the workpiece is very less, then single pulse, single shot, you can make hole. For large thickness, you have to use multiple pulse. This is a percussion drilling. Laser beam is in fixed position, workpiece is also in fixed position, and this is a percussion drilling. And trepanning for thinner workpiece, you can move the laser beam at a particular path to make the large hole. So it's large hole on thinner sheet. Here, large hole on thicker sheet. So this is a helical beam, helical drilling. So here you have to move the laser beam and simultaneously you have to focus it at different level. So this is the helical drilling. Okay, so micro hole with high aspect ratio can be performed by laser drilling operation. Now we have done some experiment on alumina, very hard material. This type of hole you can produce. Taper hole, obviously this is a drawback for laser beam machining. Although you can focus it at different level to make the straight hole, but here if you consider the fixed focusing condition, then taper hole is observed. Okay, so here top hole size, this is 100 micron, bottom is 50 micron, and thickness 1 millimeter. So taper hole sometimes we require taper hole. So for that you can apply this laser micro drilling. And this is the hole drill by excimer laser. 50 micron thick polyamide sheet and 55 micron hole is drilled, and array of inkjet nozzles. So inkjet nozzles and for that you require array of holes, and size is 55 micron, thickness is 50 micron. So that is done by excimer laser and material is polyamide. So you can refer this journal. Now cutting, if you compare with other type of cutting, laser cutting with plasma cutting, flame cutting, water jet cutting, etc. So laser cutting plays important role. Here the laser cutting has excellent performance so far as surface finish is concerned, and cut width is also very less, micron range. So laser cutting has excellent performance so far as minimum cut width is concerned. Okay, and then contour shape, laser cutting with the help of CNC control system, you can cut any kind of shape. And then different material, as I told, it can be applicable for plastic to diamond, but investment cost is high, so performance is poor. Okay, so you can compare with other, okay, plasma cutting, flame cutting, water jet cutting, but in various aspects the laser cutting has very excellent, very good performance and excellent performances. Now this is very important applications. Stent cutting, cardiovascular stent, which is used for repairing the heart blockage, artery blockage. So this type of structure, or this type of micro features are to be generated. These types of micro features are to be generated on the stent material. Stainless steel 316L. This is the low price stent material, but nowadays we use nickel titanium alloy, nitinol. Okay, so that can also be cut by laser. Now here, this cardiovascular stent micro features are generated on cardiovascular stent by fiber laser. Okay, so on the flat surface you can create this type of feature, and then you bend it and weld it, you make this type of circular tube, or directly on the cylindrical surface of the circular tube you can create this type of micro features by laser beam machining. Okay, so this can be cut by fiber laser, this can be cut by Nd:YAG laser also. Now nickel titanium tubes, micro machining, this type of group, this type of cut is possible by laser. Okay, so for that you have to control the cutting path, and here the cutting speed is also very high. You see, 5 millimeter per second. Okay, and number of pass is 5. You can change the number of pass. Okay, so different advanced material can be machined by laser. Now polymeric material, that is this is a super alloy Ti6Al4V. This super alloy can be machined by fiber laser. So in our laboratory we have done a lot of experiment to produce micro groove. Size is less than 500 micron. Micro groove on Ti6Al4V. Okay, that is done on by fiber laser. So average power is 30 watt, pulse frequency 50 kilohertz, and number of pass 8. Here scanning speed is very high. This is the cutting speed 40 millimeter per second, and thickness of the workpiece material is 1.1 mm, and this is the Ti6Al4V. sheet. Now this is polymeric material, as I was telling. PMMA, polymethyl methacrylate. So this type of micro channel we can produce by using Nd:YAG laser. Okay. Here you see these are the process conditions. Lamp current. This is a lamp pumped Nd:YAG laser system. So lamp current is there, 14.5. Pulse frequency 2.1 kilohertz. Pulse width 12.8% duty cycle, and air pressure. So here you are using air as the it's a polymeric material, and we are using air as the assist gas. Now aluminum titanate. This is one of the important material which is used for automobile industries. So this type of trapezoidal groove you can fabricate. This is 300 micron width and 100 micron bottom width and 500 micron depth. So this type of trapezoidal groove we can fabricate by laser grooving. Now this is on alumina. This type of groove on alumina, ceramic material. Now this is the groove which is generated on ceramic. This is a cylindrical surface. You can produce this groove on cylindrical surface. Okay, micro groove on cylindrical surface. Now this type of ramp, okay, and this type of microfluidic channels. These are microfluidic channels. Okay, these are the wall, micro channel, and these are the ramp. This type of micro features, those are required for microfluidic application, can be generated by excimer laser. So this is for this is applicable for telecommunication devices. Okay, so this type of applications, micro features applied for microfluidic as well as telecommunication devices, excimer laser can be applied. And three-dimensional laser micro machining, where we can remove bulk of material by using single laser beam or multiple laser beam. So two laser beam intersecting at 90 degree or less than 90 degree. So two laser beam can cut the material and chunk of material can be removed at a time. So bulk machining. Okay, because laser machining, the machining rate is less, but if you want to remove the bulk of material, then you have to apply two intersecting laser beam. Okay, this is for three-dimensional laser machining. But single laser beam can also be used, similar to milling. You can make the groove. Now laser micro turning. So we have done a lot of experiment in this area, laser micro turning. So here the workpiece is cylindrical, it is rotating. Okay, it is rotating with respect to this particular axis, and it is also moving along the axial direction. But laser is fixed, and it will remove the material, thin layer of material from the cylindrical surface. Okay. So in case of conventional turning, we use single point cutting tool, but here we are using laser beam. Okay, and workpiece is rotating as well as workpiece is moving. We are giving the feed by moving the workpiece along this direction. So thin layer of material is removed. Now there are various processes: laser beam average power, process parameters: laser beam average power, peak power, pulse frequency, workpiece rotating speed, assist gas pressure, percentage of overlap and Y directional path overlap. So there are two types of overlap, lateral overlap, longitudinal overlap. So we have to control the overlap. This is very important when you are going for micro machining, turning, or marking, etc. So here you see that percentage overlap 0, no overlap. These are the laser spot coming. Okay? But if you reduce the scanning speed, then there will be overlapping. So you can increase the overlapping. Okay, and here in this way you are increasing the spot overlapping. Okay, so percentage overlapping should be more than 50% for effective or efficient machining purpose. Now here we have turned ceramic workpiece material. Okay, and here we observe rough surface RA value. Here you see 10.47. Okay, but if you want to reduce the surface finish, so we have to defocus it. Sometimes we require defocusing, intentional defocusing, to improve the surface finish. Okay, but required surface roughness is also important for some of the applications, say dressing of the grinding wheel, cylindrical surface dressing. So for that we require rough surface. Okay, now microstructuring by excimer laser. So these are the different types of microstructures produced by excimer laser. Krypton fluorine laser, as I told, these are excimer laser, krypton and fluorine combination. So this laser produces this type of microstructure. See, pyramidal structure, conical structure. Okay, so these type of structures are needed for making micro lens array. Okay, so micro lens array, so number of lens are to be fabricated, and this type of lens can be fabricated by excimer laser. Okay, so this type of array of different structures can be fabricated. Okay, now laser marking, as I told, laser marking, there are two types of marking. One is marking by surface removal, that means by removing the material you can mark, or by modifying the surface you can mark. There are certain lasers and certain material combination. When the material is subjected to laser beam, then its color is changed. By changing the color, you can mark the surface, or by removing the material you can make one line. Okay, and by producing different line, then you can make surface. Okay, mark surface. But laser marking is a permanent marking. Okay, there are various types of marking, but chemical embossing, etc. But here laser marking is a permanent marking, and we have done a lot of experiment for fine marking on ceramic material, and this is the system. But for marking, one thing is important in the system: laser beam should be moved. Okay, laser beam should be moved or tilted. So there is galvanometric scanner. By this you can tilt the laser beam, and that is required for marking. Now again, for marking, spot size important, and then scanning speed you have to control to achieve this overlapping. Okay, so here for marking, the percentage of overlap should be more than 60%. Okay, higher the percentage overlap, better the marking at quality. Now, here you see this is the line marking. Okay, fine line with 59 micron and depth 52 micron. Here the marking intensity is very high, 78%, 0.78, and this is on ceramic material, okay, alumina. So this type of mark is possible, mark of different logo, letter, number, etc. This type of logo, sorry, on zirconia. Zirconia is the ceramic material. Now, alumina, zirconia, aluminium. So we have marked and also we have optimized the conditions of machining. Okay. Now we can also mark the laser surface. We can mark the surface. Okay. We can mark the line as well as you can mark the surface. For logo generation, this type of surface, circular surface, okay, we can mark. That means we can remove very thin layer of the material in this type of shape. Okay, this is the microscopic view of laser mark surface, and this is the surface roughness tester to check the wettability, etc. So this is the surface finish. Now this type of logo you can mark. We have in fact tried to make the hallmark. In jewelry industry, laser marking is very common nowadays. So this type of mark on metal, stainless steel, actually we have marked on stainless steel this type of logo, okay, hallmark or is SBI symbol. Okay, so laser writing of 2D data matrix. So this is the glass material on which the marking is done. This is a close view. Okay. So this type of data matrix can be marked on glass. So here we can you can see the mark on the egg cell, expiry date, and mark on the pad, cell phone read pad. Okay, color marking is also possible by laser. Okay. Now laser dressing. So dressing is required to avoid the problem of loading and glazing of grinding wheel. So mechanical diamond dresser can be used, but laser can be applied for assisting this dressing, mechanical dressing process. So laser assisted dressing or directly laser dressing. So laser can apply to remove the ground chips, okay, or it can also dress the abrasive grain to actually remove the bond and expose the abrasive grain, trace abrasive grain, okay, and it can also remove the ground chips loaded on the gap between the two grain, okay. So laser dressing is another application where you can generate rough surface on alumina wheel. So laser dressing is another application. So here you see this is a schematic diagram. Used wheel before dressing, mechanical dressing, this type of structure, and laser dressing, this type of sharp abrasives you can achieve. Now, so I think time is over. Hello, may I continue or I will stop here? Hello. Am I audible?
Sir, sir, you can continue, sir.
I can continue. Okay. Now, I have tried to explain different laser machining where the laser beam is used to remove the material. Okay. But there are certain applications where the laser is not removing the material, laser is assisting to remove the material. So that's why it is laser assisted machining. Actually, the material removal process is different. It may be mechanical type or it may be advanced machining, but laser beam is assisting to enhance the material removal rate or to increase the surface finish condition. Okay, so laser assisted conventional machining where the laser is used before turning. Laser is used to soften the workpiece material. Okay, sometimes the workpiece material is very hard and it is very difficult to turn because it requires very high cutting force. But if the laser is applied before turning, it will assist the material removal. That means it will soften the workpiece material and then conventional turning can be possible. Or laser assisted milling, laser assisted dressing. I told just previous slide, laser assisted dressing. Mechanical dressing is there, but laser will soften the workpiece material. So here the combination of laser and conventional machining. But laser assisted advanced machining, there are various advanced machining like electrochemical machining, electric discharge machining, water jet machining, etc., where you can use laser beam to assist the machining process. So these are all hybrid machining process. Okay, assisted hybrid machining process. Now here you see laser beam is falling over the workpiece. It will soften the workpiece material and then conventional turning tool is applied. Okay, so here you can use laser beam assisted or turning operation. Now laser assisted turn mill. So you can use milling operation, but before that laser beam is applied, it will soften the workpiece material and then it will be easier to mill the surface. Okay, so reduction of cutting force. You can reduce the cutting force, you can improve the surface roughness. Okay, and the researchers has already recorded the result where there is reduction in cutting force and improvement in surface roughness when you are using laser assisted milling operation. Now laser plus micro EDM. Okay, so here you see that pre-machining by laser ablation. So large number of material you can remove. Initially you can get the shape. After that you can perform finishing operation by EDM. Okay, so here the laser is used and here the ablation rate is very high, but EDM is used for finishing. By using EDM you can remove the recast layer which is developed by laser. Okay, so this type of combination, laser plus micro EDM. Similarly, laser plus ECM or laser assisted jet electrochemical machining. This is also another area where jet ECM is applied, but along with the jet the laser is supplied. So when laser is applied, then temperature increases and there is a enhancement of the rate of chemical reaction. So as a result, the material removal increases. So that is another combination, laser assisted jet electrochemical machining. So here you can improve the material removal rate and precision and accuracy can also be improved. Now here you see, this is ECM, electrochemical micromachining and laser. These are combined. So here you see, this is the electrochemical machining, micromachining, and then laser is applied. So this heat source removes the oxide layer. So oxide layer formation is detrimental for electrochemical machining. But if you use laser beam to remove the oxide layer, then oxide layer means it is a passive layer, then the electrochemical machining rate can be increased. That means current flow increases, electrochemical reaction dissolves the material, and then final finishing by electrochemical micromachining, and this is the final workpiece. Okay, so if the laser beam is applied, then there is a localizing effect. So laser beam improves the localization effect in the small area, and it increases the effective machining rate and precision, better accuracy and productivity. Now laser assisted water jet machining. So this is the laser beam and this is the water jet. So these are combined, CO2 laser and water jet. So here it improves the surface quality and as well as the cutting efficiency. Now here the laser beam is actually passing through this nozzle and along with the water. Okay, so there is internal reflection at the water air interface, and the researcher has recorded the result, and they have mentioned that surface roughness can be in the range of nanometer, 150 nanometer for the laser microjet process. So there are various combinations for laser assisted machining. Now finally, for machining application, different types of lasers can effectively utilize: CO2 laser, Nd:YAG laser, fiber laser, diode laser, excimer laser, and there should be proper selection of laser micromachining process parameter as well as the laser, and optimization of process parameters are very much needed to achieve high dimensional and geometrical accuracy to serve advanced machining applications. Then laser machining technology, as I told, it is widely used for micromachining applications, micro drilling, micro cutting, micro grooving, micro turning, marking, laser dressing and cleaning, etc. for varieties of advanced material. And in laser assisted machining processes, laser softens the material and laser beam assists the material removal in assisted hybrid machining process. Now these are the references. Now this book, in my lecture at the end, I refer, because this is our book, myself and Vijay Bhattacharya. We actually published this book. This is an authored book, Modern Machining Technology, and it focuses on advanced hybrid micromachining and super finishing technology. And this is published by Academic Press of Elsevier. So you can consult this book, okay, for this advanced machining as well as laser beam machining. So thank you. I have taken extra time. Sorry for that. So any question?
Any question from participant side? Any question? Thank you so much, Dare sir, for your
Okay.
enlightening the knowledge in the area of different type of laser machining process like laser grinding, laser turning, laser marking, grooving, and in this brief session, and you have covered lots of new advancement in laser machining process like laser assisted ECM, laser assisted EDM, and other jet machining. I think all the participants have acquired the knowledge about this laser machining process. Thank you again, sir, for accepting our invitation and sharing your valuable time and deliver the lecture in our MTP. Thank you, sir.
Okay, thank you once again, Professor Deo and Professor Santosh, for inviting me in this particular faculty development program. So I think there is no question. That means all things are understood, or they can go through our book or any material, or if they are interested, then they can contact me later on also, email or WhatsApp. So thank you once again for
Thank you.
organizing this type of FDP. I have gone through your lecture schedule. This is a very nice organization covering almost all the topics related to advanced manufacturing processes. So thank you, sir.
Thank you, sir.
Thank you. Okay. So shall I leave?
Sir.
Okay. Okay. Thank you.
Thank you, sir. Thank you.